Hello, everybody, and great welcome to the new year 2026. We start with the inaugural lecture by Ivan Smalyukh, and he will talk on artificial matter from knots, solitons, and vortices in chiral media. Ivan, to you.
Thank you so much, Renzo. It's a really great pleasure. So thank you so much for this invitation. And today I would like to start from these words of Rich Feynman, who say that what I cannot create, I do not understand. And of course, this is one of the inspirations for us to recreate analogs of natural phenomena in different systems, and especially in the systems which we can access experimentally. So here you can see hierarchy of different length scales and time scales in relation to different physical phenomena. Of course, many of them cannot be very easily studied experimentally, but analogs of these phenomena can be recreated in the experimental accessible systems like condensed matter systems. And very recently, people got inspirations to also create analogs of atoms, for example, and with them to create metamaterials that would have properties not accessible in natural material systems, such as negative refraction of light, such as negative refractive index, and so on. And today in this my talk, I will discuss with you how we can use knotted vortices as analogs of these atoms and cosmic strings that you see here in this diagram, and also how we can create crystals of knots and observe giant electrostriction, how we can fuse and observe fission of different knots as well as their different dynamics. And toward the end, I will show that just like with these metamaterials we see in here, we can use knotted vortices in optical and isotropic liquid crystalline materials to control beams of light, including to tie them into knots. And I would like to start with an interlude to beautiful history that I'm sure everybody in the audience is aware of. The modern knot theory has very interesting origin. Long ago, as we know, Lord Kelvin was thinking about the physics behind the periodic table of chemical elements that you can see in here. And he had an idea long before people even universally accepted that atoms exist. He already was thinking about models of what atoms could be. So he was thinking perhaps those could be knotted vortices. And in this process, he introduced the beginnings of what is now the modern knot theory, a major branch of mathematics. But also he introduced the concept of chirality because, as he was looking at knots like these trefoil knots you can see in here, he was thinking whether from the standpoint of view of them being analogs of or atoms, they are the same or different knots. And so you can see that this beautiful model that was proposed originally by Lord Kelvin was giving a lot of inspiration to many people around that time in Scotland some 150 years ago. Here you can see an example of that, a poem by Maxwell, one of the most famous physicists. You can see writing not only Maxwell equations, but this beautiful poem and many other poems. And within it, you see also embedded a lot of science that we understand. And reading these poems, we can admire that already at that time, they could understand a lot of the things, for example, that in 4 dimensions, all knots can be untied. But we know that atoms, actual atoms, are something different. and the either in which the model was proposing that the vortices would exist does not exist itself. So, this model turned out to not describe the real physical atoms. However, in the modern physics, we do see a lot of analogs that have some connections to this model. So, for example, there are models of globules that are composed of gluons solely, that could be described as knotted solitons. Also, in cosmology, there are theories that would predict existence of knots throughout the history of the universe. And also, we know very, very good example also where the physicist Ed Wheaton could contribute to the development of and understanding of the knot theory by providing insights from quantum physics, right? So this is actually the work of physicists, the only physicist that was recognized by the Fields Medal. And what I would like to discuss with you today is more of how we can look for insights into knot theory also from the perspective of experiments. And we know that unknots in vortices can be created even by dolphins. You can find these beautiful videos that you can watch and enjoy in the internet. But physicists recently were able to use 3D printed structures to also be able to produce knotted vortices in water and in other media. As you can see, for example, in this beautiful video by the group of William Irvine at University of Chicago. However, these knotted vortices are not stable in this case. They eventually decay to knots and disappear. And this already provided a lot of inspiration to modern pure mass theories. And here I just show some examples of the beautiful works that these experiments inspired. But how about stable atom-like knots that we could observe and perhaps even use to create some materials with unusual properties? And so today I will discuss with you how we can create all kinds of knots in soft condensed matter physics and materials that are made of little rod-like molecules similar to the ones that you have in the screen of liquid crystal display that you might be looking at right now viewing this video, this seminar. So these liquid crystals are very commonly utilized in different modern technologies, but we will now dope them additionally with colloidal tiny nanoparticles that are under 10 nanometers in thickness and only about 100 nanometers in diameter, and they can be magnetically monodomain. Moreover, they can align in our sample preparation in such a way that the magnetic moments point along the molecular orientations of these liquid crystal molecules in the dispersing host medium, and then they interact and would be parallel to each other, forming this magnetic colloidal system where the mutual orientations of these magnetic moments give origins to magnetization field. And these type of material systems have very facile response to external magnetic fields. For example, dramatic switching of such systems can be done by just 10 Gauss of field. Even Earth's field is making a strong effect on such systems. Moreover, we can also observe all the kinds of phenomena that we are familiar for solid state magnets, such as magnetic hysteresis loop, all kind of different magnetic domain walls and so on. Furthermore, by doping this type of liquid crystalline colloidal dispersions with chiral molecules that have mirror symmetry breaking, and because of these chiral carbon centers you see in here, we can obtain chiral analogs of these systems where magnetization is twisted into the helical states, as you can see in here. And so now what's very interesting is that we can describe the energetics of these systems with the Hamiltonian that you can see in here, describing different terms of different types of deformations you could have in magnetization field. Splay, twist, band deformation, and then we have this additional chiral term in here. Moreover, these type of systems also coupled to external electric fields and magnetic fields, linearly to magnetic fields and quadratically to electric fields. And what's also interesting is that in one constant approximation, which is reasonable for these systems, if we take these different elastic Frank constants to be equal to each other, we can actually, with these notations, with these notation relations for the different constants in micromagnetics, Hamiltonian, and liquid crystal free energy functional, we can actually see that this free energy functional can be mapped to the micromagnetics Hamiltonian for one constant approximation, and with the exchange constant equal to half of the average elastic constants and Zoloshinsky-Maria constant related this way to helical wave number and the average elastic constants. And actually, we can engineer by forming different mixtures of liquid crystalline materials the systems where such constants would be indeed equal to each other. And therefore, we have a model system that can describe this micromagnetic Hamiltonian type of phenomena also in liquid crystalline colloidal systems. So indeed, as we would have originally the helical background that I was showing you at no applied fields, as we would then apply electromagnetic field along the helical axis, we can form this conical state, and then at even higher fields, we can obtain unwound states in both pure liquid crystalline systems and in the ones which are formed by dispersing these magnetic monodomain nanoplates. So what's interesting is that in both Hamiltonians, we see these chiral terms, Zoloshinsky-Maria term in magnets, colloidal magnets, and chiral term in our soft matter systems. And these terms are extremely important for what I will discuss with you today, because they stabilize these twisted structures, and they will be essential for formation of all kinds of stable vortices and not solitons. And so now this helical axis in here is the axis around which the molecules twist or the magnetization field would be twisting around. But in the large sample of liquid crystal, we can have regions where this helical axis is not well defined. So you form effectively a defect in a helical axis field. And this defect we can refer to as distwistination, perhaps in analogy to disclinations along which orientational order is disrupted, or dislocations in which positional order is disrupted in other physical systems. So here, the twist directionality, the chirality is locally disrupted in this system. So now what's interesting, we can tie these type of objects into knots in the helical axis field, as you can see in here. And as we would observe them in experiments and numerically model based on the free energy functional that I was describing to you, we can see very, very good agreement between the experimental observations of these objects between cross polarizers and the computer simulated images that we obtain based on free energy minimizing functionals. As we change applied voltage, because of this facile response I was mentioning, these objects will morph quite dramatically, as you can see. But in all cases, they are stable, and we can see that we can reproduce their structure and capture their configurations and images in the computational modeling. So in the helical axis field here we have a knot, and this is why we named these type of structures after we observed them as helinotons, because these are helical field knot solitons embedded in the helical structure, like the one you can see in here of the liquid crystal system. But when you would look at the director field or magnetization field of the actual system, the material field that actually describes orientation of molecules or magnetic nanoplates, we would see that this is nothing else but the physical embodiment of Hopf vibration in the liquid crystal order parameter field or colloidal magnet order parameter field. So those are elements of the third homotopy group, pi 3 of S2 equals Z. And so in here we have such a Hopf soliton that we studied some time ago in the liquid crystals and magnetic systems. And you can see in here the structure of these objects in deep details. So everywhere within this three-dimensional volume, the magnetization field and molecular alignment field are continuous. There are no singularities in orientation of those fields, as we would take all kinds of cross-sections of this type of objects in with three-dimensional structure. And then as we would, however, look at the helical axis field, right, we see that there are regions where orientations of helical axis are discontinuous, and those are these distwistinations that I was referring to earlier on. And so now what's interesting is we can have such objects in liquid crystals and soft matter systems like colloids, but we also numerically modeled them in magnetic solids such as iron, germanium, and MnSi. And in them too, we predicted in this paper and here that they would be energetically stable under some conditions. With what's additionally added in this case, that because of the quantum nature of this system, we also have the emergent field that you can see in here that can have quite interesting Hopf vibration looking like structure as well. Moreover, we could compute Lorentz TEM transmission electron microscopy images that actually led to the discovery of this type of solitons. Just actually the article in Nature Materials was published about 2 weeks ago, so now they are also experimentally observed in magnetic solids. So as I already mentioned, the objects that we look at in here are the elements of the third homotopy group, the hopfions, right, from the homotopy theory classification. And they are three-dimensional topological solitons, analogs of the Skirm solitons that, as we know, have been used to describe subatomic particles with different baryon numbers, where this integer z would correspond to actual baryon number. And these solitons were originally proposed in particle and nuclear physics by Tony Skirm. But now in condensed matter material systems, we can realize not only baby Skirmians, two-dimensional analogs of those solitons, but also three-dimensional topological solitons, the hopfions, that have these particle-like properties. And so let's now take a look at their behavior as we would be changing applied electric field. So you can see in here between two cross polarizers in optical microscope, between two parallel polarizers, and in a bright field microscopy observation, that these type of structures, as you apply a pulse of electric field, like 4 volts, not very large field, are morphing dramatically, and their background changes around these topological solitons too. What we can do is we can numerically model this type of solitons and their evolution in applied electric field, and we can reproduce every single detail in these computational models, as you can see here at the bottom, that correspond to the snapshots from the video that we see in experiment, closely in agreement with the experimental results. And as we would look at the morphing of the pre-image linking, we see that at all times we have the pre-images corresponding to single values of order parameter field forming a Hopf link, which is what you would expect for a Hopf soliton. So the topology as under this dramatic transformation does not change, much like you would have it, in transforming this donut into coffee mug and bag. The Hopf link under all conditions is staying the same, but the geometric configuration is evolving dramatically, as we can see. And indeed, we can now compute all kinds of stability diagrams for the liquid crystals, colloidal magnetic systems, as well as solid-state magnets. And as an example here, as we would be changing electric field, and for this axis in the diagram, we would have some ratio of the constants. We can see that we have regions of stability and metastability of these solitons, as well as regions where they would not be stable. And as we would, apply voltage in this axis, we would be changing their geometric structure, but they remain topologically stable. And so, for example, in here, the embodiment is the helical background of the system, whereas as we apply strong field, just few volts, not so strong, we can go to conical background and then eventually to uniform ferromagnetic-like background and transform the geometric embodiment of this soliton between two different states, right? And as I already mentioned earlier, the pre-image linking under all of these conditions stays the same. So they remain topological solitons with well-defined Hopf index. But if we would now send a series of pulses to this system and let the system relax, with this type of configuration of voltage driving scheme, very interestingly, this particle pretty much becomes alive because it starts moving somewhere because of non-reciprocal evolution of the field configuration. And so you can see in here, it effectively becomes an active particle when we apply electric field perpendicular to the screen and have this field in the form of pulses with such a high carrier frequency and relatively low modulation frequency to allow for the structure to relax between the different states that correspond to transformations in series periodically between these uniform, twisted, and conical states that we just discussed. So what's beautiful in this case is that actually when this topological soliton is moving somewhere, it's only the molecular alignment that is evolving, but there is no material transport in this case. So you could think about this much like in the analogy with this stadium wave, where people are waving hands and the wave can be moving around the stadium, but people stay in their seats. Very much similar to this in liquid crystals and magnetic systems, we can have this type of motions of these topological solitons that involve just rotations of this molecular alignment field or magnetization field. And now, however, I would like to proceed to demonstrate that they can not only show this transformation of the structure, but also behave very much like atoms or molecules would. You can see in here the Brownian motion that these topological solitons undergo between two cross polarizers, and as we would study their diffusion it would be very much similar to what you would expect for a colloidal particle or a molecule, right, in a fluid medium. And then, as we would observe these objects and move them with laser tweezers, we see that they can rotate and translate, in different directions. And when we have many of them, they can form, for example, an analog of a gas of these topological solitons or a liquid, right? Where under some conditions, no applied field, we see no strong interactions between them. Yet, as we would increase the applied field, we can switch that structural, effectively liquid or gas type of system that has no strong interactions between topological solitons into a crystal where these topological solitons start strongly interacting with each other and crystallize. So here I show how we can change the applied voltage just within the range of few volts. And with that, we can change the strengths of interactions from a K Boltzmann T or so to tens of thousands of K Boltzmann T. So very broad range. And you can see in here that they can interact over shorter or longer distances, attracting each other or repelling each other. And we can tune the potential of interactions in a very broad range. Moreover, this can be in 2D when we have some confinement, but also in 3D, as you can see from this video in here. And this already shows you that we can do things with these quasi-atom-like particles that we could not do potentially with conventional atoms. When it comes to conventional atoms, there is little we can change in how they interact with each other, what the strengths of interactions or anisotropy, but we have all the power that only God could have for real atoms when it comes to controlling interactions of these objects in the liquid crystal host medium. And here there are more demonstrations. So I'm applying 1 volt or so change of voltage, and you can see the change of lattice parameters. In the example at the bottom, you can see that we can not only change the lattice parameter, but also with a bit higher voltage, we can change the symmetry of their self-assembly into this crystallite. You can see here going from unidirectional to anticlinic orientational order between them. And I want to remind everybody that these are knotted solitons, that they are not going away or disappearing. They are stable and they can be controlled, and they exhibit giant electrostriction where the lattice parameter in one direction changes by over 50%, and the other direction only very, very little. So we have giant electrostriction. Conventional atomic and molecular systems have electrostriction on the order of 0.01%, but these knotted metamaterials have, as we can see, 50% or so anisotropic lattice change. Not only we can form the self-assembled tightly packed crystals that are more common in conventional molecular systems, but also open lattices that you could not achieve with atoms or with molecules, and are very hard to find, for example, in colloidal systems. But here they form under some applied voltage conditions very easily. And I already demonstrated different lattices that are changing under applied field in 2D and in 3D, and forming these different crystalline lattices that can self-assemble into all kinds of structures, including the lowest symmetry triclinic crystals of these solitonic nodes. But what I would like to discuss with you next is a little bit more of exploration of analogies when it comes to the atoms that we know about, right? And for example, we know that the nucleons within atoms can undergo fusion and fission, right? And these are either current or future sources of energy in nuclear plants. And so what we will, however, do next is apply electric fields much like you can see depicted in here, similar to what you do in your laptop screen, looking at this presentation, applying electric field on pixel by pixel basis to demonstrate information. We will now apply such field to the samples with knotted vortices and see what will happen, right? Could we perhaps somehow fuse them, and how exactly this fusion and fission processes would proceed. And so here you can see a video as we would have the same notes I was describing to you earlier, but now instead of 3 or 4 volts, I apply 5 volts at this frequency of 1 kilohertz, right? So very normal, very easy to have such applied fields. I can see fusion of these nodes. Now I want to ask a question, what really happens? Because I would love to resolve all the details of such structural transformation that you see here in this video. And well, for that, we need to apply an advanced technique of three-dimensional imaging, mapping of these director and magnetization field configurations in 3 dimensions. For that, we use an optical setup utilizing femtosecond laser sources and phase modulators that you can see in here built in our research laboratory in Boulder. Now, with the help of this system that is, as I mentioned, built around the femtosecond laser source, we can obtain supercontinuum femtosecond laser light and shape it with the help of spatial light modulator. Then these pulses of femtosecond light can be sent to the microscope, and we use them to generate different types of nonlinear processes, including multi-photon absorption-based luminescence or second harmonic generation or third harmonic generation or the coherent anti-Stokes Raman scattering. So I will not go into details of all of these nonlinear optics processes, but what they allow us to do is to image orientations of such molecules. For example, based on orientation of transition dipoles in the process of luminescence based on 3-photon absorption. And that allows us to visualize then the three-dimensional structures of the field, and from them we can reconstruct all kinds of pre-images. So as an example, here you can see predictions based on our own modeling for how these different images should look like if we have a certain types of topological soliton, the hopfion in this case. And you can see that theoretical model that we developed and simulated those images very closely matches the experimental results, right? You could say they are agreeing quite closely to each other. And based on this type of images, we can reconstruct now pre-images corresponding to the different values of the order parameter field. So for example, for these diametrically opposite orientations of the magnetization or director field, we would have a Hopf link that you can see depicted in here. That's based on computational modeling. We would expect, by minimizing free energy, to obtain this type of view of pre-images. And indeed, this is what we observe in the experiments. And little by little, we can reconstruct all of the pre-images one by one within the three-dimensional volume corresponding to such three-dimensional topological soliton. So now, what should we look for in these systems when we want to see some processes of fusion, like I was showing you in the video a few minutes ago? So we know in pure mass there are the beautiful concepts of the connected sum of nodes and the topological surgeries and how could we perhaps, also observe them in experiments? And indeed, when we have the knotted vortices that I was showing you before, we can visualize them in different ways and observe these processes. So now I will be showing you these vortices in two different ways. On one hand, the structure of the vortex line within which the helical axis field is undefined, but material field of magnetization or molecular alignment is well defined and is colored based on this S2 order parameter space. And you can see that within these vortex nodes that we have here, we have different colors, right, corresponding to orientations of this magnetization field. And when these nodes are fusing in our experiments and computational models, they come together to have the same orientation of the magnetization field or director field. And you can see that as we apply voltage, two nodes can fuse together to become a single node, which is effectively the connected sum of nodes that I was showing you earlier. So in this visualization, we visualize magnetization field, but in a similar way, we can also visualize the deformations in the helical axis field that actually correspond to singularity in this chi field that you see in here, and see how the inner structure of these vortices is changing during these reconnections in deep details. What's more is that we can actually apply pulses of electric field, as you can see depicted in here, and observe sequential events of fusion and fission of these nodes, right? So every time the pulse arrives, they fuse and then they undergo fission, and we can control it under the conditions very similar to what you have in a display that you're looking at right now. We also observe that there is some response time on the order of a fraction of a second that corresponds to these nodes transforming from individual ones to a single node and then back. And these type of transformations, to many of us, pretty much make the drawings from the node theory books go live, very much like in the famous movie Night at the Museum. All the exponents were becoming alive at the midnight. Right now we can see these type of transformations between the nodes and the details of fusion and fission in these type of structures visualized in here with the different approaches and that correspond to, for example, the two individual trefoil nodes going through the process of fusion with two reconnections taking place at the same time, and then additional reconnections in the end giving us this multi-component link that you can see in here. For some special structural configurations, we can even establish simple relations between the Hopf index of the topological solitons and the crossing, the minimum number of crossings that we could have between within the vortex line. So establishing very simple relation between the different topological analogs, that different topological invariants that describe these dual nature knotted structures. So again, I'm showing here examples of fusion and fission, right? And all of this, as I mentioned already, happens by just applying a pulse of electric field. And it has the analogy to the known phenomena in nuclear physics. So nuclear fission, we know, is widely used in nuclear plants these days. It's an important source of energy. Nuclear fusion could be even better future green source of energy, but is still under development, as we know. these extremely difficult processes to achieve in conventional atomic systems, but in our analogs, we can just of atoms, we can just apply pulses of fields and observe them undergo fusion and fission, and we can model it computationally based on minimizing free energy, forming all kinds of parameter space diagrams. And what's beautiful is that experiments are very closely captured by computational models. As you can see, the comparison between the two plots, and here, where we observe these transformations that correspond to the fusion of the two trefoil nodes, and the very same sequence and angular dependencies and images are all very well captured by our numerical models. So I mentioned before that we can sequentially fuse and separate the nodes into individual ones by applying pulses, like the ones you can see in here. And this can be done for a variety of different nodes. By changing voltages, apply it to the system, you can actually control the different transformation sequences and different relinking sequences that can happen within this type of systems. And I am here just summarizing the diagram the different types of band surgeries that could describe our observations that we had for a pair of trefoil nodes. And now imagine that you fuse not just two nodes, but many of them. For example, you could take this fused double node that we obtained by fusing individual trefoil nodes and fuse it with another trefoil node and obtain yet more complex composite node, and so on. You can fuse sequentially more and more knotted objects, and you can see in here the computational models showing how the different relinking can happen in these different systems. And so as an example, yet another example in here, we can see fusion of nodes that can lead not only to multi-component links and complex nodes, but also to graphs where in some cases physically these type of structures do not fully get resolved, right? So we have some nodes of the graphs, as you can see in here. And as we fuse more and more nodes together to obtain even more complex nodes, by using the help of laser tweezers, we can move these nodes around and we can control the precise locations where these fusion events happen. And so here's yet another example of a complex node fused from an array, also controlled by the laser tweezer system. So what's interesting is that we can start from individual nodes and then apply higher and higher voltages and observe them undergoing fusion and fuse many more nodes, for example, 1, 2, 3, 4, 8, 18. And you can see in each case we obtain much more complex multi-component links and graphs. But then you could ask a question, how to relate these very complex knotted diagram structures to the notion of atoms, where you would expect some integers that would correspond to atomic numbers or perhaps baryon numbers. And what's interesting is if we take the integral that you can see in here to compute the Hopf-index topological invariant, we find that it stays constant, unchanged, when we have individual nodes or the fused connected sum of these nodes, right? And so as you would fuse, for example, 18 nodes, 18 of them separately had Q equal 1, and the sum of them was 18. But when it got fused, even though you have this very complex knotted structure that you see in here, the Hopf index topological invariant stays conserved, as you would expect, similar to fusion and fission that we have in nuclear and atomic systems. And as I already mentioned, interesting observations also correspond to these different graphs with, for example, four-valent vertices where they can be resolved into different states of knots. So you could think about them as superposition of different knotted structures. Well, up to now, I was showing you a lot of playing with different types of knots that are stable, so we can do a lot with them. They don't go away. We can control their self-assembly very much, controlling different lattices, symmetries of them, fusing knots together. But how about material properties that perhaps this type of systems could enable? And here, actually, I would like to demonstrate that such objects allow us to control light in a very interesting, unusual way as well. But what's more is that we can build on analogy not just to atomic and nuclear physics, but also to cosmology to get some insights into this behavior. And so what we have first, let's look at the vortex line, which is in here perpendicular to the screen and has this kind of structure of molecular alignment, which is depicted by little rods. And this is now, I want to remind everyone, optical anisotropic material. So when light will propagate in it, it will split into ordinary and extraordinary modes, and it will see different, the extraordinary mode will see different effective refractive index depending on orientation of the k vector, the propagation direction, relative to the liquid crystal director's or optical axis orientation. And so now, if we want to ask, as you send a laser beam, for example, entering the sample here at point y1, how exactly it will propagate through the medium? Well, to get to point y1 prime, the light will try to find the path that corresponds to shortest amount of time that it needs to get to that point. And this is stemming from the Fermat principle. Light takes the shortest amount of time to get from point y1 to y1 prime, and so on for the other points too. So when you look at these propagation directions, which we computer simulated, you can see what effective refractive index the light will see as what will propagate through this medium. And we can now present it on a cone, as you can see in here. And when we do so, we see that actually the deflection angle that you will have in the end when light is passing by this vortex line will be some delta phi, which is related in a very simple, interesting way to the geometry of this cone, right? Sorry, I went wrong direction. To the geometry of this cone. Well, now we can make such a vortex line in liquid crystal, and so this is what we would expect. And these are the experimentally obtained trajectories of light propagation. As you will send the beam from left to right, they will be deflected in a way that is very close to that what you would predict computationally. But there is more. If you send these beams of light and you overlay the experimental results with the computational modeling, also analytical modeling, you see very good agreement, but you also see very good agreement with prediction from cosmology for how the rays of light would be deflected by the cosmic string that would be here in the very same location. So the red lines and the dashed yellow lines correspond to liquid crystals and cosmology respectively. And you can see they overlay one on top of each other pretty much perfectly because they are described by the same equations, the same Fermat principle type of based physics, even though they are in two different systems. So in the case of cosmology, people have been fascinated by cosmic strings possibilities all the way from the time of Keeble making his proposal back in 1976. And what's interesting is that people have been looking for these type of cosmic strings based on the gravitational lensing type of experiments. Recently, people are looking and seemingly have good evidence for existence of cosmic strings based on gravitational experiments. But so as light would propagate next to cosmic strings, it would be deflected in a way similar to what I was showing you minutes ago for liquid crystals, because of the cone geometry that is exactly the same. Because in this case, the cone geometry arises from the very heavy mass of this cosmic string, where in just 1 foot of length, you would have the mass corresponding to the sun, right? Very, very heavy, mass density of a cosmic string. Then Allah gives origin to the gravitational lensing, and very interesting because of that cone geometry in both liquid crystals and the cosmological systems, we have the same equations describing these two phenomena. Now, what's interesting is as we would plot that deflection angle in liquid crystals as a function of delta n, which is optical anisotropy, and extraordinary refractive index divided by extraordinary refractive index. For the cosmological systems here, we have the gravitational constant, the mass, linear mass density, and the speed of light. And you can see predictions of the two theories overlap on top of each other, the dashed blue and red lines. There is departure from those two only at large values of delta n over ne, which you cannot achieve in cosmological systems anyway. And you see from this also that the cosmic string can steer light more than very heavy extraterrestrial objects like sun, or the heaviest steering objects like quasars. But liquid crystals can deflect light into even larger angles. And you can see here different material systems we worked with, right, that could deflect to even larger angles because of the optical nature of these materials. So now, not only we can localize, we can use these vortices to steer beams, but we can also create crystals of them. And you can see here the images of those in experiments and in computational modeling, and we can localize beams of light, pretty much circling them, to be localized, as you can see in here. And moreover, by engineering the structure of knotted vortices in liquid crystals, we can also knot the beams of light, not just to unknots, but also to knotted trajectories that you can see depicted in here. And so this is interesting because the phenomenon is related to cosmology. It's inspired in many ways by cosmology in our experiments, but at the same time, it is truly enabling for the next, generation optical engineering of different types of optical material systems. For example, for all kinds of virtual reality, augmented reality type of applications, this could be extremely interesting. And while we are not developing time machines, so not developing, yet maybe this could inspire somebody to think about these possibilities. And I don't know if you're aware of this interesting article from long ago, but having the ability of localizing light and having analogs of cosmic strings and material systems, can think big, about all kinds of applications and model systems in material systems. So this brings me to the conclusions. I hope I was able to show you that we can obtain stable vortex knots and topological solitons and chiral nematic and colloidal liquid crystal systems, as well as solid state magnets, and they can behave as analogs of atoms or subatomic particles. They can form also all kinds of crystalline self-assemblies and lattices, and they can undergo the processes of fusion and fission. They exhibit emergent dynamics that can be paralleled with behavior of active particles as well. And I showed you that connecting to not only the particle and atomic physics, but also to cosmology, we can develop these systems as metamaterials that can allow for steering light and localizing light into closed loops and knots that is not easy or possible with conventional materials, or even metamaterials that would be obtained by nano engineering of different types of optical structures. And with this, I would like to refer back to the beautiful history that gave the very origin of knot theory, the Kelvin's idea. It's true that the real atoms is something different than what he proposed and the idea that he had. But in many ways, this idea was a solid physically sound idea. And instead of thinking about it as a blunder, because the actual atoms are actually something different than the vortices that are noted, we can now think about his original model as a topological metamaterial design principle that could allow us to manufacture new types of materials with properties that natural systems do not have. So I would like to thank you for your attention, and I'm happy to answer questions.
Wonderful, wonderful talk, and extremely interesting, and exposing many aspects that I'm sure trigger many questions from the audience. Thank you very much, Ivan. I ask those who wants to put questions to come alive and switch on your mic, and please put your question to Ivan. I may start with one question, Ivan, if I may. Actually, I have many questions, but first of all, can you just comment? You show the Hamiltonian at the beginning, and made of several terms, of course, and the two terms they differ in terms of a quadratic term, and I'm referring to the chiral contribution, which is we may call it helicity density, or Hopf, of course, density. Can you say which term is more important and which term is less important in this Hamiltonian? I understand that it depends very much also on the input energy that you put in the system to control these various terms. And then a very fine point is, what is this Q0? Because I can see K22 playing roles in these two terms, and then there is a Q0 in front of the K22 term.
Thank you. Very good question. So he is a general liquid crystal Hamiltonian that describes all the deep physics. Because all of these constants are measurable for different materials, and you would actually find experimentally the values that they correspond to. And the micromagnetic Hamiltonian, in a similar way, is just simpler, right? It has two of these constants in here, which also can be measured experimentally. And so I mentioned what's very interesting is that as you take all of these constants equal to each other and then call them K, and with this relation, right, you actually map this complicated Hamiltonian to a little bit simpler one that you can see in here. And the
Sure.
chiral term effectively remains in the similar form. So the Loshinsky-Maria term in here. So without this chiral term in the two systems, the material would want to have uniform magnetization or material alignment field. So pretty much like what you see in here, right? Because all the deformations, all the distortions would cause some energy, and the system wants to minimize the energy, so it would just form a uniform state. When you have this chiral term, then of course you can form the helical state, the conical chiral state, and as I was showing later, this very same term is also stabilizing all kinds of solitonic and knotted vortex structures because it provides a tendency to twist, right? Makes it energetically favorable. And then as you will additionally apply external fields, for example, magnetic or electric, you can control these interplays, right, between the different terms in here. And so, the chiral term is extremely important for the stability of all the objects because we know there is Derek and Hobart theorem, which says that topological solitons in linear field theories are not possible. But as you would add nonlinear terms or chiral terms like in here, then you effectively overcome the constraints of these topological theorems. And so then we can find energetically stable particle-like topological solitons, including three-dimensional hopfions that I was describing and helinotons.
Thank you. I have another quick question, and it's about the fusion mechanism that is very, very beautiful. As you surely well know, the mechanism of, let's say, reconnection for classical vortex dynamics involves the anti-parallel, most of the time, anti-parallel orientation. Can we talk about oriented or anti-oriented strands locally?
Indeed we can. Moreover, in here, there are even other phenomena that might go a bit beyond, for example, other media, right? Because of the type of orientational polar or non-polar ordering that we would have in here. And so to illustrate this, interesting observation, I want to draw your attention that, in some of the places we have these, dark black fragments and in some a little bit gray, brighter fragments, right? And when these two nodes are undergoing fusion, right, in here, through these reconnections, very interestingly, the fragments with opposite winding number, local winding number in the cross section would co-align, and then effectively they annihilate each other locally, and then provide this source for reconnection that then would be proceeding with applied pulse of electric field.
I see. I remember a piece of work that Dewitt Sumners and I did a long time ago proved that locally, across reconnection, you have conservation of writhe. So is a is just across
Mhm.
the reconnection
Mhm.
event.
Mhm.
Do you have any information on
Um,
this?
Yeah, so indeed, when you undergo such a fusion in here, it is conserved. But you can also have later many more complex reconnections, like as, for example, at this later stage when it would not be conserved. So, yeah.
And when you go to these very complex knots, composite knots, as you saw, for example, 18 or something like
Yeah.
that,
Yeah.
you mentioned the Hopf index, the Hopf number remains conserved. Can you please say it again? What is conserved is the initial Hopf index, or
Yeah, well, so if you would look at the individual knots or knot solitons, which are hopfions in material field, right? Direct
sure,
magnetization, each of them will have a Hopf index 1, right? That would correspond to linking of preimages that correspond to single values of order parameter field, right? And
sure.
that linking geometric interpretation of that index would be just one, right, in all of these cases. So you have many Hopf links, but as you will make them fuse, what I was showing is mainly related to vortex lines in the helical axis field. But there is also another thing that we are now describing related to what happens to preimages. And indeed, as you form this very complex knot, you get very large linking number that corresponds to 18. And you can see it also numerically integrating the whole volume, right, and getting that topological invariant through numerical integration as well.
Hmm. Wow, quite amazing. Uh, okay, maybe I have to be quiet and ask again if there are questions from the audience.
May I ask a question, Renzo?
Oh, hi, Keith. Sure, you can. Please go
Volunteer.
ahead.
First, thanks, Ivan. This was a brilliant, fascinating talk you've given. I'm sorry I came in a little bit late, so I missed the some of the introductory remarks. But I was glad to see that you came back to Kelvin at the end of the
Yeah.
lecture. But in classical fluid mechanics, vortices, we think of vortex tubes that have a cross-sectional structure. And I wasn't sure if your vortices have that cross-sectional structure that plays a part, or if you're treating them simply as curves in 3D. Can you
Yeah.
comment on that?
Absolutely, yeah. So, yeah, well, so first of all, indeed, I was connecting to beautiful history because that's a big inspiration for many of us. But indeed, as we would look at these vortices in the system I was describing, they have very interesting structure, right? Because in the material field, there is no singularity. So all the molecules are smoothly changing orientation, and all the magnetic moments of nanoplates are smoothly changing orientation. But as you would look at the helical axis field around which these molecules twist, you would realize that that helical axis field has a singularity. And in here, it's not defined, right? So then we would call this type of field, this type of vortex line as distwistination or discorrelation in analogy to disclinations that describe disruptions in orientational order or dislocations that describe disruption of positional order. And these type of objects, right, even though you could have the polar magnetization field or non-polar molecular alignment field, these helical axes have non-polar nature, right? And so you can have this kind of effectively half integer defect line in the helical axis field. And that, is very rich because you could have them of different type, either plus 1/2 or minus 1/2. And I will show you some reconstructed configurations, and they can annihilate, and they are playing an important role in all the reconnections that I was discussing later on. So as an example, when we get to look at these lines, right, you will see that the structure of these fields, right? This is the helical axis field. Here it's disrupted, and it can have this local 1/2 or -1/2 nature. And as you would go along the line, it can change from 1/2 to -1/2, because in 3D, this is allowed, right? And so in the helical axis field, as you would look in the material field, like magnetization, it's everywhere uniform, but you can nevertheless display the orientation of that field in the course of these vortices. And you will see that when these objects reconnect, the connection happens when the colors match. So no singularity is introduced additional, during this process, and yeah, so.
Okay, thank you.
You're very welcome.
Other questions, please.
Hello.
Since I can, yeah, please. Hello.
Yes.
Hi.
Thanks for the talk. I have a very maybe basic question that I missed. What are the actual liquid crystals? So what's the material that all of this is?
Yeah,
That you manipulate into knots.
Yes. Very good question. So I had some chemical structure, but honestly, we can work with many different materials, and we play with also mixtures of them. The physics we describe is general, so it is just slightly changing as you change material systems. Okay, a bit too far. So take a look at this type of molecule, right? In our display, you have many such molecules without this chiral carbon center in here, right? And actually, the mixture of 4 of such molecules with different lengths, is a very common system that was used over decades in displays, right? And so they are rod-like molecules. For physicists, we can approximate them as little rods. When you have a chiral center, then it's a little bit different from rod. It has some chirality in it, so perhaps little screw, right? And then from them, you can make these type of materials, right? You just mix them. Because of all the applications, including liquid crystal displays, electro-optics, the chemists produce many different materials, and that allows us to control all of these elastic constants I was describing to you, right? For example, make the mixtures that would actually correspond to them being roughly equal to each other. And so, we essentially we can benefit from all the developments of liquid crystal technologies, which, by the way, add to something like $1 trillion per year globally, right? So it's more than GDP of, like pretty much top 20, number 20 country, right? And GDP listing corresponds to this kind of liquid crystal industries cumulatively per year globally. And then, these are the molecules. So we play with many of them, different types. But then there are also these nanoplates. And so these barium hexafluoride nanoplates that can be synthesized through hydrothermal synthesis to be made magnetically monodomain, like these little hexagonal disks with under 10 nanometers in thickness and magnetically monodomain. So as you make the system of dispersing one in the other, then adding chiral molecules, then you just play with all the conditions and fields, and you observe everything we see that I was describing.
Yeah, thank you. That gives a good idea. Thanks.
Thank you. Very welcome.
Other questions, please.
Excuse me, Ivan. Yeah, may I just raise a question? First of all, let me just thank you for this wonderful talk. Very exciting. Yeah, thank you. My question just to follow Renzo's second question, focusing on the connected sum of knots. Can you just turn to the page of
Yeah.
connected sum of something here?
Yeah.
Yeah. Here, if we just read the top left corner, we can see the connected sum of two treble knots. For example, they are both left-handed. For example, both left-handed. Renzo and I, we are just writing a paper giving a kind of definition to measure to tackle the complexity degree of knots. According to our thinking, if we just combine two left-handed same chirality treble knots, then the complexity degree will increase. But if you just connect one left-handed and the other right-handed treble knots, then the complexity will decrease. So my question is, have you tried to connect two, opposite chirality knots? Yeah.
Yeah, very, very interesting question. Perhaps I didn't have a chance to, connect to a very interesting interplay between chirality at different hierarchical scales, which is very interesting. So you know that we have chiral molecules, right, which have these carbon centers I was telling you about, right, and they have some handedness at the molecular level corresponding to just carbon center of the hydrocarbon chain. And then you have the chirality of liquid crystal, which is matching that chirality of the chiral molecules. And then we embed the chiral knots in it, and that chirality is matching the chiral. So, what we played with were all homochiral knots, and so we could produce more complex. So essentially, you are getting more and more complex stuff. No
Yes,
reduction of
sure. Yeah.
complexity in this system. But I want to mention that, in relation to your question, there is a way of engineering it in a different system where, we recently play with so-called band core molecules that can form twist band phases. And in there, it is good to twist, but twisting to the left and to the right is kind of equally good. And then, in this type of systems, we still did not do everything we hope, but I think there, what you're thinking about combining knots of different handedness actually could be possible, different chirality. And
Thank you so much.
the other question is, which perhaps could be also of interest for many people in this community is, as you are combining them, is it possible that at some point, the medium is chiral, but the knot that you could form through some fusions, combinations, relinkings could become amphichiral, as an example, right? So, yeah. So those are really beautiful, interesting questions to pursue.
Yeah. Thank you so much. Yeah.
Thank you.
That brings up the idea, we know from nature, some systems in nature, that when you go from the chirality of a helix into reversed the orientation of the helix, which is technically called perversion, if you check on the energy is higher when the filament goes in one way and then reverse its orientation. But this depends, of course, on the physical and the natural phenomena. I wonder if something like this might happen, i.e., going from preferred twisting direction and then reversing the twisting engineeringly done this way. If it is very expensive, I mean energetically more expensive or not, I have no idea about that.
So it's a very nice question you're asking again. And so there are types of structures, these chiral dopants, right? I showed you one simple one, but there are the chiral molecules that can reverse chirality. How this happens is through some transformations, cis transformation in the backbone of these molecules, that reverses chirality because of, conformational change in response to shining light, like UV light, for example. And actually, there are even such materials. You might know of Ben Feringa, Nobel laureate in the Netherlands, who was synthesizing molecular motors, right? So there are again systems like that, where essentially you can use light to control chirality of the molecules. And if you would do that in liquid crystals, you would you would be able to change left-handed liquid crystal, unwind it, and wind it to be right-handed. But all of it will happen at once, right? So still, referring back to Shin's question, I will have either left-handed or right-handed trefoils, right? And the complexity will always increase. But if I want to have left-handed and right-handed, the other system I mentioned, right, where energetics allows for different twists, with equal energies, that might be a route. Yeah.
Thank you very much. Other questions? Okay, we took great chances to put questions to you. Ivan, thank you for your time and thank you for this wonderful talk. Thank you very much. Thank you.
Thank you. My pleasure. I enjoyed communicating and I really enjoyed the series, so I often watch, the videos, although typically, just videos posted on the on the website. So yeah, thank you so much.
Thank you again.